All right. Now, I just wanted to show you the formulas that are involved in these different kinds of heat transfer. We're not going to do any mathematics where we plug numbers into these formulas, but I just wanted you to be aware that there are formulas that go with each of these different kinds of things. So again, let's review. Conduction is going to be the movement of energy through a material, but the material itself does not move very far. Now, it can vibrate. In the case of a gas, I forgot to mention it, but here is a gas, and so conduction would occur in a gas when this molecule here gets very, very hot, so that means it's moving very fast. And so let's say it slams into this one, and then this one then gets the energy, and maybe it slams into this one, and then this one in turn slams into another one over here. So do you notice that when this one hits this one slows down and basically stops. And then this one goes forward, and after it hits this one, it stops. So these molecules are not moving very far again, but the slamming is what's being transferred like this. Another example of that is like, it's called Newton's cradle. Maybe you've seen it where it's got a bunch of balls that are next to each other, and then you take one ball and you lift it up and you let it go, and then when it hits this ball, it hits the one next to it, which hits the one next to it, and then this ball over here jumps out. So it's the same principle. Notice that the individual balls aren't moving very far, but it's the collision that's being transferred through the material. So again, that's what conduction is. So here is a material, and it's going to be like a pipe, a solid pipe that has an area A on this end. The length of the pipe is going to be L, and then this side over here is going to be hot, and then this side over here is going to be cold. So this is going to be at a higher temperature than this temperature over here. So the rate at which the heat goes through the material, so this is the amount of energy per second. So T for time, Q for heat. So the amount of heat per second that goes through this rod depends on what is the rod made of. So some materials are better conductors than others. So that's what the C is. So that's going to be the conductivity, the thermal conductivity of this material. Then it's also going to depend on the area that it's going through. It's going to depend on the length, and then it's also going to depend on the change in temperature of the material. So that's how we would calculate the rate at which the heat would move through this material. Now let's compare that to, and then again, here are some thermal conductivities for common materials. Okay, now let's compare that to convection. So in convection, you're going to have this boiling pot of water, and notice that the convection, instead of being sideways, as it was in this picture, is going to be up and down. So that's going to be the rate at which that heat is traveling through the water. So we're going to use the same Q over T. It's going to depend on a constant. So this time it's going to depend on like the viscosity of the water. So some water is able to flow easier than other kinds, or some fluids flow easier than others. So it depends on a constant. And then notice it depends on the area, A. So this time the area is going to be the area of the top of it. So there's your pot, and then the area would be that thing there. And then the convection is moving in this direction. And notice that there is no L this time in the formula, but it does depend on T. So that the hotter it is down here compared to up here, the faster the convection is going to occur. All right, and what about radiation? So radiation is going to be the flow of the heat in the form of light, and that light could be radio waves, infrared, X-rays, gamma rays, whatever. And so our formula is, it's still going to be Q over T, so the rate at which the heat flows in the form of light per second is going to depend on what is the light flowing through. So this is going to be another constant. And then you can see it's also going to depend on the area A. And it's also going to depend on the temperature, but this is where it gets a little bit different. So you might notice it's not just temperature to the first power, it's temperature to the fourth power. And we're not going to get into why that's true, but you can look it up on the internet and look at a derivation of that. But it does depend on the temperature raised to the fourth power. So what does that mean? If you were to double the temperature of something, how is that going to affect the rate at which heat is being given off by it? So 2 times 2 times 2 times 2 is 16. So that object, if you double its temperature, will give off 16 times the amount of heat per second than it did before. So, last thing that I wanted to mention to you is this idea of Newton's law of cooling. So all three of these are Q over T's. All three of them depend on area A. All three of them depend on temperature in some manner. So that this means that in the case of a house, the greater the temperature difference between the inside of the house and the outside of the house, the faster the heat is going to flow. So if you increase the change in temperature inside the house versus outside the house, that makes the heat flow faster. So what does that mean? During the winter time, if you turn down your thermostat, then that means that there is less of a difference in temperature between the inside and the outside, which means your heat is going to be lost less, or the rate at which the heat flows through the walls of your house is going to be less. It's also going to depend on what are the walls made of. So that's the C again that is in there. It's also going to depend on the thickness of the walls. So that's going to be the L in this case. And then it's also going to depend on the area that the heat is flowing through the walls. So normally you can't change the area of the walls. Now you can change the thickness of your walls, and you can also change the amount of insulation that you put into those walls. So all of this is going to help you with your utility bills. Okay, so we're finished with this lesson, and now it's time to take our lesson quiz when we return.